The next problem that we are going to deal with branch and bound technique is knapsack problem. So in this problem, you will be given a set of n items and each item is associated with a weight and a value. You will be given a knapsack of capacity m. The problem is to find set of items that fits into this knapsack with the sum of the weights of these items should be less than m, and at the same time it should end up with a maximum profit. So since this is maximum profit, it comes under maximization problem, and in maximization problem, instead of lower bound, you will be calculating upper bound. So in TSP it was minimal cost, so minimization problem and lower bound. Here it is maximal profit, so it is maximization problem and upper bound. So here are the steps that are to be followed in solving this problem. First, you need to find the ratio of value and weight of each item. Then, second step, you have to arrange these items in the descending order of the ratio of value by weight. And then you have to calculate the upper bound by using this formula V plus M minus W into Vi plus 1 by Wi plus 1. So this V is the value of the item. This M is the capacity of the knapsack. W is the weight of the item. Whatever item you are considering, this is the ratio of the next item. Since it is specified as Vi plus 1 and Wi plus 1, if I am considering the value and weight of the first item, then this will be the ratio of the second item. If these are for second item, this ratio will be for the third item, and it goes on. So we will solve an example for this problem. So here is the problem. You are given a set of 4 items, each one associated with the weight and value as depicted. The first step is we need to find the ratio of value by weight. So you have to divide value by weight. So it will be 10, 6, 5 and 4. The second step is you have to arrange the items in descending order as per this ratio, that is value by weight. But in this case, it is already in descending order. It is already in descending order. So we need not do anything. We need not modify anything. Straight away we will go for the calculation. So the upper bound is calculated by using this formula. So initially, let us start drawing the state space diagram. So the state space diagram will be like this. Initially, no item is added. So W will be 0. So value will also be 0. What is the upper bound? Upper bound is calculated by using this formula. So it is 0 plus 10 minus 0. Since no item is considered here, this Vi plus 1 by Wi plus 1 will be the ratio of the first item. It is 10. So 10 into 10, answer will be 100. So upper bound in this case is 100. Then I can include item 1 or without item 1. So it is with 1 and without 1. So when item 1 is added, W will become 0 plus weight of the first element. It is 4. Value will be 0 plus value of the first element. It is 40. And now the upper bound will be V plus, that is 40 plus M is 10 minus the weight into, since I am dealing with the first item, this portion should consider the ratio of the second item. So it is 6. So 40 plus 6 into 6. It is 36. So the upper bound will be 76. And without 1, what will be the weight? I have not included 1, so weight remains 0. Value also remains 0. What is the upper bound now? So it is 0 plus 10 minus 0 into, I am dealing with item 1. So the ratio should be item 2. So it is 6. So 6 into 10 will be 60. So upper bound is 60 here. Of these two, which one should I explore or which one should I proceed with? Since I'm dealing with maximization problem, I have to select the upper bound with maximal value. So this is the one which is to be explored. So already I have considered item 1. Now it should be with item 2 and without item 2. So how will it be? So with item 2, already the weight of the knapsack now it is 4. What is the weight of the second item? 7. So if I include 7, it will be 11. 11 is greater than the capacity of the knapsack. So this cannot be explored further. So I am leaving it. I am going for the next option without 2. So if I am not including 2, weight is going to be the same 4. Value is going to be the same 40. What is the upper bound now? So upper bound is, we all know, value plus, that is 40 plus m. M is 10 minus weight is 4 into, since I am dealing with item 2, the ratio should be of item 3. It is 5. So 40 plus 6 into 5. 6 into 5 is 30. It is 70. So upper bound is 70. So of these, which one to explore? 70 only. So obviously I will explore this. So it is with 3 and without 3. So if I include 3, already the weight is 4. Here the weight of third item is 5. So 4 plus 5 will be 9. And the value is, already it is 40. Here it is 25. So it is 40 plus 25, 65. I need to calculate the upper bound now. Upper bound is V plus 65 plus M minus W, that is 10 minus 9 will be 1 into, since I am dealing with item 3, the ratio should be of item 4. It is 4. So 65 plus 4 will be 69. So the upper bound here is 69. Then so without 3, weight will remain the same as 4 and value will remain the same as 40. Now I need to calculate the upper bound. So it is 40 plus 10 minus weight 4 into, since I am dealing with item 3, the ratio should be of item 4. So it is 4. So 40 plus 6 into 4, that is 64. So upper bound is 64. So of these two, which one should I explore? The maximal one. So I am exploring this. So this is with 4 and this is without 4. So when I include item 4, already 9 is the weight. If I include 3, it will become 9 plus 3, 12. 12 is greater than 10. It is not acceptable. So this is not the solution. Let me come here. So without 4, weight will remain 9. Value will remain the same thing. And what is the upper bound? Upper bound is V plus M minus 9. That is 10 minus 9 will be 1. I am in fourth item, but there is no fifth item. So what will be the value of Vi plus 1 by Wi plus 1? It is going to be 0 only. So 65 plus 0 is 65. So the upper bound is 65 here. So I have checked or explored all the items here. 1, 2, 3, 4, all the items has been explored or considered, and the weight here is 9, which is less than the capacity of the knapsack. So this is my optimal solution. So since I am dealing with maximization problem, maximum profit, all other leaf nodes which are less than this can be killed or can be considered inferior. So this will become inferior since it is lesser. This also becomes inferior since it is lesser. So in the above problem, this is where we find the optimal solution, and we have to traverse from the root. So I have included item 1, excluded item 2, included item 3, excluded item 4. So in item 1 is included, 2 is excluded, 3 is included, and 4th is excluded. I have represented ones in terms of ones and zeros, and the profit will be the value which is there in upper bound, which is 65. Hope you understood the concept of knapsack problem. Thanks for listening.